So thank you so much, everybody. And here's Tim. Thank you, Tim.
Hi, everyone. I'm happy to fill in tonight, and I'm going to just try to do the thing here. There we go. How does that look? Okay, so this isn't a terribly long talk, but it's a very interdisciplinary, and I guarantee there will be some fun images of crystals and a little bit of mineralogy. The talk is a result of that horrible smoke that filled the air in June. And the work that we did was spurred on by our volcanologist, Ben Andrews. And these are my colleagues here, Tim Gooding and Rob Wardell, who also helped with the imaging and analysis and the study of just what is in wood ash. Something that 3-4 months ago, if you'd have told me I would know a lot about, I would have never imagined that I would, but it happened. So what would you do when a volcanologist colleague, Ben Andrews, says we should compare the ash from the Canadian wildfires with volcanic ash so people know the difference? Well, what do you do? Well, the answer is you do an experiment. So setting this off, was the terrible, terrible smoke that we had in June and again later in the month. You can see the difference in these two pictures taken on Pennsylvania Avenue, downtown Washington, D.C., just 8 days apart. From my office at the museum, I can, on a normal day, I can see the Capitol dome. During this time, I could not. So there's where the fire was up in Canada. You can see where we are. And who knew that there was an air quality index that was greater than code red, code purple, but we actually hit code purple during that time. By the way, this is totally informal talk. Ask any question anytime. So what exactly?
Hey, Tim?
Go ahead.
This might not be something you know about, but on the map that you just showed, I noticed that there is a sizable gap between the location of the fire and the maximum air quality, or maybe I should say minimum air quality, around the mid-Atlantic. Do you have some idea about why that appears to be the case?
I think, Jeff, this is a meteorology question more than a geology question.
Yeah, I did say it might be something you didn't really know about. So
yeah, sorry, I cannot shed any light on that.
Okay, thanks anyway.
It is a curious thing, though, isn't it? But yeah.
It seems to me that it might just be a snapshot of a particular day. Perhaps a day earlier, the red was a little further north.
Sure.
Well, that could be.
But I just remind everybody, if you want to ask him a question, you need to unmute yourselves.
Okay, so the first question is, what exactly happens when you burn wood? Well, if we're going to be looking at ash particles from wood, we need to kind of know what's happening. So we do a little research and find out that wood is basically 95% carbon, oxygen, and hydrogen, and that's mostly cellulose. And if the perfect combustion of pure cellulose happens, and that formula there in the left in the middle there, C6H10O5, carbon, hydrogen, and oxygen, is what cellulose is. And if you throw some oxygen at it and you burn it, basically, you end up with two things, carbon dioxide and water. Great, but the problem is that plants have other stuff in them. So we need to do some more preliminary research. So we go to where else? Wikipedia. And we look up composition of wood ash. And we get this sort of very generalized tabulation of what is in wood ash. And these percentages here are percentages, I presume, of weight percent, but I'm not even sure what kind of analysis this is, but that doesn't really matter too much. What it shows is the sort of major and minor elements on the left that are in the wood ash, and then the trace elements on the right. And the ones to look at mostly are, of course, carbon. You would expect that. Calcium. Potassium is particularly interesting. Magnesium, manganese, phosphorus, and sodium. Those are all pretty common in varying amounts in wood ash, depending on what kind of tree or plant has been burned. The fun one, of course, is potassium. And some of you probably have, maybe you have, but I certainly have used wood ash in my garden as a potassium source for plants that like potassium. And you do a little more research and you kind of find, oops, I'm sorry. And you find some stuff online and in articles that are published about wood ash. And here we have some pictures and some X-ray spectra, which I'll explain a little more about later. But the X-ray spectra are analyses of these grains that you see in the picture on the left. And isn't it interesting that some of these grains kind of look like crystals, don't they? And if you look at the elements that are labeled in the three spectra, K is potassium, Ca is calcium, you see P, there's phosphorus, you see silicon in in the spruce spectrum, and up there in the pine spectrum, you see particularly high peak for potassium, that's K. Anyway, that's all very interesting and was actually quite surprising to someone who knew nothing at all about what the composition of ash from wood is like. And so I point out that the scale bars on those images on the left, the top one says 10 micrometers and the bottom two say 50 micrometers. But what is a micrometer? Well, it's a millionth of a meter. So if you think of a meter long stick, which is bigger than a yard, bigger than 3 feet, and that's 1/millionth. A micron is 1/millionth of that length. A human hair is about 50 microns. So that's about the size of the scale bars that you see on the bottom two images. That's the yellow bar that you see over here. Okay, so these chunky things here are about 10 microns across, much smaller than the thickness of a human hair. Anyway, that's pretty cool. People have studied this stuff before. Of course they have. So what we need to do is design an experiment. We have terrible smoke in the air. And so the volcanologist says we need to go out and collect some of this stuff. So what are we going to do? So we took this tray, actually 2 of them, and my colleague Rob Wardell designed this collection apparatus. And you can see there are some watch glasses there and some glass slides, and then you can see 3 black round discs on the left. Those are 1-inch round sticky discs that we use for studying all kinds of things. We'll stick a sample down on that black sticky material and stick it in the analytical SEM for study. So who do we get to do this? Well, of course, we send the summer interns up on the roof of the building, and there you can see them with the collection apparatus. And in the background is somewhere down far away is the capital of the United States. It's somewhat shrouded in the smoke. So we put those in the east parking lot of the museum as well as on the roof. And we left them out overnight. And so that was the basic design of the experiment. And then we brought in the samples, and we only ever looked at the little black 1-inch round discs. And so the instrument that we used to look at the materials that we collected is this relatively new, 1.5-year-old analytical scanning electron microscope that you see here with a couple of my colleagues, that was purchased for the express purpose of studying this asteroid material that you see in this poster on the back wall. That's the asteroid Bennu. And in less than a month, in fact, in like about 3 weeks, a spacecraft will come hurtling down to the Earth in the American Southwest with a significant amount of material from that asteroid. And we will be one of the first labs to actually get our hands on some of this material. The sample that's in the instrument right here, when I took the pictures, actually newly released soil, or regolith, they call it, from the moon that NASA released about a year ago, and some of our scientific staff have been studying. And so there's actually a piece of the moon inside the instrument when this picture was taken. And pretty soon there will be something even more exotic from the asteroid Bennu. And we've been preparing for the better part of a year, learning how to use this new instrument to study that very, very precious material coming back from Bennu. So, you know, another thing that you can do, if you happen to have a source of, wood ash, is you could go get some of that and look at it before you even look at the stuff that you think you're collecting from the smoke. So I went out to the back deck and grabbed some ash from apple wood from my smoker. And we took it in, we set it, put a sample in the microscope, and the first thing we saw were crystals. How about that? Where on earth did these crystals come from? Many of them have this interesting spongy character. You'll notice that there's also some other material here that's not nice crystal shapes. Pretty neat. I had no idea that right there in my backyard, I was actually sort of making, or we'll see pretty soon, modifying crystals. Up close, it looks like the crystals are actually a lot of smaller crystals. So there's a 10-micron scale bar on that picture. So that's 10 millionths of a meter. Really, really tiny. And so we analyzed that material, and look what we got. So this is an X-ray spectrum. We utilize the X-rays that are emitted from the sample When the electron beam hits the sample, X-rays are given off, and we're able to separate those X-rays by their energies, and then the machine automatically gives us nice labels to put on them. And we found out that, in fact, the crystals from my smoker are calcium carbonate. And notice there's a little potassium there. I can't tell you which form of calcium carbonate that is from this analysis. It could be calcite, it could be aragonite. I don't know. I just know that it's pretty pure calcium, oxygen, and carbon. And that makes it calcite or calcium carbonate. There was also, by the way, a little bit of charcoal left. And this is what charcoal looks like under the scanning electron microscope. You can see there's cell structures still. This has not been completely burned. So I'm jumping ahead. So now we have the first sample from the east parking lot. And the first thing that we saw that we collected on one of those black sticky dots was something we knew absolutely nothing about. Not that we knew anything about wood ash either, but the first thing we saw were these pollen grains. Okay. Wow, that's cool. There they are. Those are 10 micron scale bars on that picture. So once again, these are really tiny. And so the first thing I did was I gave a call to Conrad Labandera down in paleobiology. He's a paleobotanist. And I said, Conrad, can you come up and look at these pollen grains? We knew they were pollen, but that's about it. And he said, those look like some kind of conifer pollen. Okay, great. And he said, you know what these sac-like structures are on the side of those pollen grains? And of course, we didn't know. And he said, they're sacky. Perfect, right? They look like sacs, and in fact, they're called sacky. So we also enlisted the help from our botany department folks, and they indeed corroborated that these pollen grains are from pine trees. Not only that, they're probably from a white pine. And we know that white pines had finished their blooming cycle a month or two prior to the smoke invasion. So what does that mean? Well, it means that we're actually collecting something on our little black disk that's not from Washington, D.C. at all. It has to be from somewhere to the north where white pines were blooming at the time. You do a little bit of research and you find out that in June, in Maine, white pines are blooming. So this is pretty good evidence right away that we actually did collect something from the smoke from Canada. Pretty neat. But then we started seeing some other really interesting grains. And here we have one of those, kind of a wispy, wild looking thing. That's 100 microns across. So that's 1/10 of a millimeter on that scale bar at the bottom. And what on earth is this? Well, it kind of looks like some of that stuff from my barbecue grill. Here's another grain of that. Now, if you think about it, we were breathing this. Pretty jaggedy looking stuff. Here's another one. They're actually pretty neat looking. And the next picture is the blow up of the rectangle. There you can see there's some crystals, and a lot of this stuff looks like it might be amorphous. I'm actually not sure, but it may be non-crystalline, almost glassy-like material. So should we analyze it? Yes, we should. And lo and behold, we're seeing another X-ray spectrum. showing us the elements that are in this material. And similar to those spectra that we saw from that earlier slide from different woods in a different fire, we can see that we have all the usual suspects that were in those: carbon, oxygen, magnesium, phosphorus, chlorine, a little bit, that's interesting, a bunch of sulfur, and of course potassium, a large amount of potassium, and calcium. So that's kind of neat. It means that we're getting similar results to other scientists, which is always reassuring. But then we started seeing crystals as well. And here you can see a cluster of those crystals. And it also has attached to it some of that wispy looking material. So we know that it's associated with that. And similar to the material from my grill in the backyard, you can see that these crystals are sort of spongy. And if we were all together, we would be eating Rice Krispie treats, because that's kind of what it looks like, and I would have brought them with me. Here's another cluster of crystals. Now remember, that's 20 microns wide, so that's less than half. That's 20 microns across from here to here. So remember that that's less than half the width of a human hair. And this crystal probably, I'm quite confident, came from the wildfires in Canada. So that means, you guys, that we were breathing crystals from Canada. How about that? Unless maybe you were wearing a mask, and that would have been probably a pretty good idea. Here's one last picture of a bunch of crystals, and we had Jeff Post come into the lab when we first saw these, and the first thing he said, we told him that it was calcium carbonate, but he said that's not a shape for any calcium carbonate mineral. Well, he would know, right? So what on earth are these crystals? Well, they are calcium carbonate, and using another instrument called a Raman spectrometer, we were able to actually nail it down to being the mineral calcite. So once again, nice calcium, carbon, and oxygen in the X-ray spectrum. So where do these crystals come from? And so we have to do more research, and we find out that wood contains calcium oxalate, which some of you may know as a horrible human malady called kidney stones. But calcium oxalate also is produced in wood in nature. And here you can see some pictures of those calcium oxalate crystals that I swiped off the internet. And sure enough, they kind of look like the same shapes as these crystals of calcite that have the wrong shape. So the problem is the crystals in the ash are calcite, not calcium oxalate, but they don't have the shape of calcite. So what's going on? Well, here's what happens. Calcium oxalate, which is calcium plus carbon and oxygen, CaC2O4 that you see there on the left, reacts to become calcium carbonate plus carbon monoxide. So if you heat up calcium oxalate in a fire, it will become calcium carbonate plus carbon monoxide. But carbon monoxide is highly flammable and readily becomes carbon dioxide in the fire. So that means what we have is replacement, a change in the composition in the solid state, which actually is kind of the definition of metamorphism. But we're just going to say the crystal shape remains true to the original mineral, and it becomes calcite, a calcite pseudomorph of calcium oxalate. Now, I think Andy Thompson has a question now. Andy, are you there?
Yep, just unmuted. Yeah, thank you. The question I had was whether in doing your research, whether you came up with some really odd crystals that may have not been wood-based, but may have been other materials. And the question comes from left field from another person. But the idea is, do you find some surprises with regard to materials that were not wood-based? Because we're talking about this coming from basically the forest fires in Canada.
So that is a great question, and I'm glad you asked it yesterday, and that's why I knew to call on Andy. But anyway, yes, this was a setup, but it was very good because I had forgotten to talk about this in the slideshow here. And that is basically when you set up an experiment, there's a very, very important part of any experiment that you need to do. And that's what we call a control. Okay, so we collected this material on the roof and in the east parking lot when the smoke was in the air. And then we looked at that. And we saw not just the beautiful crystals I showed and those amazing wispy structure things and the pollen, but we also saw seeds and some other organic material and some chunks of sort of granular material. And so why don't we think those are from Canada? Well, that's a very good question. And I think that's kind of what Andy's asking is what else did you see? And how do you know that's not from Canada? Well, the answer is we did a control. So it's really important to do a control in any experiment. On people, they will give people a placebo, for example, instead of the medication that they're actually studying. And so they make sure that the people that have the placebo are the control. They're not getting the medicine in the experiment. The rest of the people are. So then they can compare the two results of the people who have the fake medicine, no medicine, and medicine. So that's an example of a control. In our case, we sent the summer interns back up on the roof after the smoke had cleared with another collecting tray, and we left it up there overnight. And so then we took the little 1-inch round disc from that collection when there was no smoke, and we were able to compare that to the samples that we collected during the smoke. And the sample had no pollen, no pine pollen, and no crystals, and none of that wispy stuff. But it did have the same granular material, which we think is part of the roofing material on the roof of the building. So in fact, the two samples during the smoke and the control when there was no smoke did have some particles in common, but they did not have, only the smoke collected particle sample had the pine pollen and the crystals and the other wispy things. So we are quite confident that those crystals, the wispy particles, and the pine pollen are not from a local source at all. And of course, we can use general reasoning that because this collection was done when the smoke was heavy, that in fact, those things that I've shown you are, in fact, little tiny particles that traveled all the way from Canada to Washington, D.C. and into our lungs. So it's a very important thing to always have a control when you do an experiment like this, so that you can convince yourself that what you're seeing is actually something that's unique to the circumstances that you collected them under, which would be when the smoke was heavy.
Thank you, Jim. That's very helpful. Can I mention one other question that Jeff raised a question about the difference between the gap between the Canadian forest fires up north, and then seemingly not much smoke and so forth. But then when you get down into the DC area, the Baltimore, Washington area, you have an immense amount of it, including going up towards Philly. And some people have said that's because of basically that's the material coming down from Canada is mixing with what's coming out of people's gas tanks in terms of carbon dioxide and so forth. And I wonder whether that fits in the formula you had in the previous slide. Indicates, mentioned that you moved from the initial type through some burning, and then it had a metamorphosis. And I wonder whether when you have the Canadian stuff coming down, plus meeting with basically the hot fumes from the congestion of traffic, whether that would have given the extra temperature boost to make that chemical transaction happen. Just a theory.
Yeah, I don't know. I think that by the time any of that material got here, it was fully cooled off. And the transition from calcium oxalate, calcium carbonate clearly happens when I'm burning wood, smoking a pork loin in the backyard. So I think most of the chemical changes in those crystals took place at the source of the fire. And of course, the tremendous heat of the fire would have wafted this material up to great heights, and then intersected perhaps, high level winds that brought it down here. Why it almost kind of concentrated on top of this, I think, is a meteorological issue and not so much a pollution issue.
Thank you.
So back to the original question, right? Which was Dr. Ben Andrews wanting to be able to show the difference to people between volcanic ash and wood ash or wildfire ash. Here you can see a couple of pictures that show that fairly well. Volcanic ash is typically or commonly made of glass shards from a rapidly quenched liquid that's blown up into the air during explosive volcanic eruptions. And as you can see, the textures are very different. You see lots of bubbles. And then you see some other grains that are very dense. So it's quite a variety, but it's very different in shape and much heavier. So the calcite crystals are nowhere near as dense as some of these really dense grains here. Either way, you can see that they're kind of spiky, and you wouldn't want to breathe any of this stuff regardless. I am unaware of anybody who's collected volcanic ash at the distances that we did. We collected the wildfire ash, but there certainly are volcanic eruptions that are big enough to deposit ash, volcanic ash, from the atmosphere at great distances. I think Mount St. Helens was actually detected. Mount St. Helens ash from the West Coast was detected in Washington, D.C. back when that happened. So I guess I misspoke, and that there have been modern eruptions in our lifetimes that produced ash, that volcanic ash that fell all the way across the country. So that answers the questions, but there's more. This is an amazing painting done in 1690 in Mexico called The Marriage of the Virgin by Jose Sanchez. Apparently, this is a very famous painting. Well, why on earth are you showing this to us? Well, painting conservators have studied paint chips from this painting. And in cross section, the paint chip, okay, so these scale bars on the top of these images are 100 microns. So that's 1/10 of a millimeter. And some of you may know that the first thing a painter does when they paint a fancy painting, at least back in the day, was to put down kind of a whitewash onto this canvas or the surface that they're painting on. And the painters and conservators refer to that as the ground. And painting conservators have seen this before, and look at what you see. So the first layer of material on the canvas is on the bottom of the image. In all three, the upper two images are different kinds of light, and the one on the lower left is an SEM image, all of the same area of the paint chip. So that's a cross section of a paint chip taken from a little corner of the painting. And if you look at the lower right-hand quadrant, look at what you see. Holy cow, those are those same spongy crystals. So the painting conservators apparently have known for years that way back in the day, hundreds of years ago, painters were using wood ash to make this ground material that they then painted on top of, or this whitewash material. And here's another example of that, also from, they say this was painted in 1650. And there it is again. You can see the crystals. And this is a famous painting in the Metropolitan Museum of Art by Diego Rodriguez da Silva y Velázquez. Pretty neat. So the painting conservators have recognized for many years that these crystals are pseudomorphs of calcite after calcium oxalate. How about that? So painting conservators are, in a way, kind of mineralogists. And the painters themselves, although they may not have known it, were utilizing these crystals in their in the formation of the ground material that they painted on top of. So I promised that you would see some pictures from Hawaii, and my colleague Abby Nalesnik, who grew up only a few miles from my house here in Montgomery County. She is a University of Delaware graduate student, soon to be Dr. Nalesnik. And you can see on the left, there's Abby on the left with Kendra Lynn, one of her mentors there, who works at the Hawaiian Volcano Observatory. And all that red stuff that Abby's looking at is explosive volcanic deposits we call tephra. And there are probably 10 different eruptions just in front of her there. This is a place that we had never visited before. You can see a very large lava flow, a thick lava flow right here, this big blocky thing sitting on top of it. It's sloping down. And this is just the very top of what we think is probably, maybe 30 to 40 meters of explosive volcanic deposits that have never been studied before. So I hate to say it, but I might have to go back to help get this big section of tephra sampled and then analyzed. On the right, you can, oh, sorry. On the right, you can see Abby standing next to something that's extraordinary. And that is a Mauna Kea silver sword in full bloom. These plants were almost entirely wiped out by feral sheep and goats that ran amok all over Mauna Kea and Mauna Loa. They were able to save them because some of the plants that they found were on the side of steep cliffs and where the animals couldn't get to them. They bloom once in their lifetime and then they die. And what you see there are thousands. Each one of those little clumps in front of Abby is hundreds of flowers. They are a remarkable thing to see. And luckily we got to go on a ride with an old friend of mine to 10,000 feet. This is at 10,000 feet on Mauna Kea. And maybe she'll tell you more about that fun trip next month. But she's a very smart young scientist, and I'm happy to call her my colleague. So I think that's it. Let me just make sure. Yep. So there you have it. There are the things that we were breathing because we weren't wearing masks when the Canadian wildfire smoke was overhead back in June. If it happens again, maybe you want to put your COVID mask back on. But anyway, so thanks for listening, and I'm happy to answer any questions.
Well, thank you, Tim. That was wonderful. I think you answered a lot of my questions. I was like, well, how does he know that ash was from Canada and not just ash from somebody burning trash down the street or some other incident? If you grew up in Pittsburgh, it could be like from the coal mine or the steel mine.
Yeah. So pollen helps, right? Finding the pollen actually helps answer that question because pine trees were not blooming in this area. And so that helps. Can we say 100% sure? Well, we can be reasonable about this, right? There was smoke in the air and it was really heavy. It had pollen from a plant that's not in bloom here, but is up in Maine at the time, which is approximately the same latitude as the fires. We didn't find it when the air cleared.
What the heck just happened?
So that should be, pretty good evidence. Is it 100% sure?
I'm in the meeting. Turn the camera on.
So anyhow, does that kind of answer your question or your concern? Of course, we're concerned with the same thing. How do we really know it came from Canada? Well, we also know that those kind of crystals come from wood ash, right? Which is what we were getting in the air at the time was smoke anyway that carried the wood ash particles down
here. Dave, Danny?
Tim, a couple things. So you almost are giving us that tour that you promised us for how many years of all your toys?
Oh, for goodness sake.
So I was going to ask us, when are you going to lead that tour? Moving on to the next question. Are those particles too small to go through a mask? N95?
An N95 would probably stop those. Yeah.
Because they're getting awful small.
Yeah, those are they would have to be wafted through the air that far. First of all, they would have gone to tremendous altitude from the heat and then picked up by the wind. But I would have to look into that. I'm not sure, but I'll bet you that an N95 will catch those. Yeah, so my cloth Hawaiian fabric mask would do no good because it would just come around it. It's not that tight. But
You know, we had that conversation all around COVID. And of course, that's a different level of decimals, but it's the same thing. Is at what point does a mask do you any good?
so bacteria are commonly 10 to 50 microns in size. Viruses, I think, are much smaller. We've seen bacteria on many samples in the lab over the years, and they're pretty sizable, but they're not grossly different in size from these ash particles, these crystals and the other wispy things. So if an N95 can stop a virus, an airborne virus, I think the answer is yes, it would stop these particles. Does that make sense?
It does. Thank you.
Yeah.
And we've missed you, buddy.
Tim?
Hi,
uh,
Tim.
you-
Cindy?
Oh.
Go ahead,
Go
Cindy.
ahead, Jeff.
Okay. Do you want to go first or?
Ladies first,
do you
Jeff.
want- Okay,
Oh, just
go
a
ahead, Cindy.
quick question. And so those other things, those wispy dendritic, beside not the crystals, but those other things, what did you guys think those were?
It's obviously a product of the burning of the wood. It matches the composition of the things that they found in other studies, and in fact, the silly Wikipedia composition that I put up there. What form it's in, I think it might be amorphous, not crystalline, kind of almost like a glassy material, and it kind of looks like that. But I have to tell you guys, we spent way more time on this than we probably should have, but it was so interesting that we had to do it. And at one point, I just said to everybody, okay, we have to stop because this kind of thing could just keep going on and on. And so for now, we have just cut it off where we are now. It's a very interesting story. We're quite confident in the story as I've told it to you. But there's so much more that could be studied. Like, for example, your question, what exactly is that stuff? Well, we know what it is compositionally, but we don't know what it is structurally. And that would take a bunch more time. And, you know, this isn't what we're supposed to be doing. But as you know, I get involved in an awful lot of stuff. And maybe sometime I'll tell you about the history of dentistry that we've been studying by looking at the fillings in the teeth of Civil War soldiers. So anyway, that's another story for another time, but just an example of the goofy stuff that we get involved in at a natural history museum. And so how could we resist when this became so interesting? But I had to just say, okay, you guys, we got other stuff to do getting ready for these Bennu samples. And so at any rate, we learned a lot in a short period of time. And like I said, I never thought I would know this much about burning wood.
Hey Tim, this is Dan over here. I think that in science, sometimes the goofy stuff that just happens is some of the most intriguing and fun. This was fascinating,
isn't it?
Yeah.
Isn't it neat? This
is awesome. I'm looking at a huge, like behind me over here, I have a calcite that's about this big, just full of, you know, cubic crystals, and I was like, yeah, kind of looks like that. It's just absolutely fascinating, and so I know this was not like the geology talk that we normally have, but I think it's just as fascinating and pretty wicked. So thanks for sharing it. Mm-hmm.
Happy to do it.
Jeff and Kathy.
Can I add something?
Go.
So I remember in June, yes, on my front porch outdoors, I smelled campfire. So the air was definitely burning smoke. But now on June 28th, I was in Minneapolis And I lived in Minneapolis in the early 1980s, so I'm visiting my sister, and the sky was white. I'd never seen the blue Minneapolis sky white. So on my takeoff from the airport, Minneapolis to Chicago, 3:02 p.m., I photographed my first picture because I want to see, well, what altitude is this smoke coming? Now, 2 minutes later, at 3:04, clearly a very white sky, not very high altitude. But then finally, 3:07, we get the blue sky. So this layer of smoke is at a low altitude. And my sister said it's chemical burn. It literally burned my eyes. It was not the smell of smoke. And so I talked with the pilots before takeoff, and they were aware chemical. So what do you think of that? What would have been in the smoke that might have been chemical?
Toxins burning in the fire.
Like I said earlier, the wood is not pure. If it was pure cellulose, you would only have two products. It would be carbon dioxide and water. Perfect burning of any hydrocarbon is going to basically result in that. But there's other things like nitrogen, there's phosphorus, there's sulfur in wood.
Okay, yeah.
And so you could get gases like sulfur dioxide, I suppose, carbon monoxide. You could get nitrogen dioxide, which is what turns the air that sort of funky brown color, I believe, when you have terrible pollution. So there are lots of what I guess I would call chemicals, compounds that could be formed in a fire. If you're standing next to a fire and the smoke gets in your eyes, it burns, right? What is that? I don't know. Somebody, I am 100% sure, knows what those gases are, but that's so far afield from my field that I'm already talking way out of my expertise here. And what I know, I have just learned in the last few months about this subject, and so look around and maybe you can find out more about what's in smoke online. I guarantee you can.
Mm-hmm. We're all science geeks, so we question every bit of anything and make it science, make it fun.
As well you should.
Mm-hmm. No, I'm really
fair,
glad you did your presentation. I was very much looking forward to it.
just to be fair to Jeff, let him ask his question.
Yeah, Tim, you didn't really say much of anything about soot from like the diesel trucks out on Constitution Avenue. I would be very surprised if you didn't see any of that with all the cars and trucks next nearby. What does that look like? How does it compare with what you identified from the forest fires? So.
I don't know what that looks like, but I can tell you that a young Jeffrey Post, now retired mineralogist at the Smithsonian, had a component of his PhD dissertation looking at lead compounds that they collected in a similar fashion to what we collected back in the days of leaded gasoline. And sure enough, just the same way that we collected these particles, they were able to collect just in downtown big city particles of lead-based pollutants that were falling out of the atmosphere, and we were breathing them, of course, just the same way. I know that doesn't answer your question, but You know, we did run the control. We didn't see anything other than what I've told you about. But we only studied the 1-inch round samples. We could go back and look more carefully for other particles, especially on the control. But we had to stop. It just, you know, too many things with tentacles going off in all directions that are spawned by this kind of study, and way far afield from what we really are experts at. But we are material scientists, and so we study materials of all kinds. I hope I never start studying lead-based particles that come from the atmosphere, but Jeff Post did many years ago.
Well, I think it was Isaac Asimov who said something along the lines of the great innate expression of science, the one that leads to new discoveries isn't eureka, which means I found it, but rather that's funny. So, yeah.
That's pretty good. Beth, you have a question.
Yeah, it's sort of a facetious one about the control. Did you hold the wind speed and direction constant with your original?
Why, of course we did. And the temperature and the humidity. Yes, it was a control of sorts, but was it a perfect control? No. But, you know, a really good control is run at the same time as the experiment, right? In this case, we couldn't do that because I guess, no, I can't think of any way we could have run the control when the smoke was still in the air.
Yep.
Because it was everywhere.
Yep.
So, you know, we did run the control, which was absolutely necessary, because we had to know for sure, you know, what particles were coming down in the air all the time. And it turned out that sure enough, we had particles from what we think is the granular material on the roof, on the floor of the roof. You know what I mean? Up on the roof, we have a flat roof and there's granular material on the roof. And some of it's small enough to have been whipped up into the air and deposited on our little collecting disc.
So it's contaminated.
So I think the control is pretty good. It's far from perfect. And yes, we would have liked to have had temperature, humidity, wind velocity, wind direction would have been good, right? Right? To know which way the wind was blowing when we were collecting, but we're not meteorologists. We're just goofy scientists that had an idea, and it kind of sort of worked out.
Can I jump in? You know, follow up on Kathy's comment, you know, that idea about smoke gets in your eyes. What sounds like a really great title for a song. But the one thing I got, Tim, is with your toys, the implications on public health go way beyond meteorology and mineralogy. And my thought is, as you're getting into particularly the volcanic stuff and the glass, that has implications in public health, and you have tools that I think they would not have. So while I understand you have to stop because that's not your job, one of those tentacles is really, really important. I really enjoy the discovery that you did or the things that we're seeing, what you're doing. But I sure hope to hell somebody else has those toys.
I think they do. You know, the painting conservators have similar tools that we have. Otherwise, I wouldn't have those neat pictures of the ground material with the calcite crystals after oxalate, the pseudomorphs. Similarly, other people who are interested in fires and stuff are responsible for some of those first images that I put up there. So one of the things that we try to do with our analytical equipment is make sure that if there's somebody around the building in another discipline, that they know that if they have an appropriate sample, we can help them as time permits in our laboratories. And that's how we get involved in so many different interdisciplinary studies. There's a lot of stories that we tell, from paleobiology to anthropology. We involve paleobotanists in our study, in this particular study, and paleontologists, so paleontology as well. So, it's our tools are very applicable to many natural science objects, and we try to let people know that we have these things and how they can be used to help them understand problems that they have and design experiments to execute on their samples.
Any other questions for Tim before we call it a night?
I have one other small question. Why were there 2 calcium peaks on your
Okay, that's a fun one. So calcium atoms are quite large, and they have a lot of electrons flying around their nucleus. Remember that you've got the nucleus in the inside, and then you've got electrons just flying all around the outside of the nucleus. And since you have so many, some of those electrons, when they get hit by the electron beam that we use to bombard the sample, some of those electrons jump out to a position that they're not stable in, and others jump out even further. And when they collapse back down to where they belong, they give off an X-ray that's characteristic of the size of the nucleus, basically. Okay, the energy that's required to be compensated for when they jump back down, you've got to get rid of energy somehow if you're going to do that activity, moving those electrons down to where they belong. And so the energy of the X-ray tells us which element it is. But you get mostly these, the ones that get bumped out a little bit, but you get some that are bumped out a little further. And that's why the one peak was much bigger than the other peak that you saw there.
Thanks. My chemistry is way back in high school, so we got to pull it into the now. Back then, we had what were called shells, where your electrons stay in this little tiny circle, and they can jump back and forth. But the whole idea is a lot different now than it was back when I was in high school.
No, it's basically that is the same story. It's the electron shells that are around the nucleus, and when the electron beam hits those, they jump out, and then when they go back down, you have to release some kind of energy, and that energy is in the form of an X-ray, and the amount of that energy is basically dependent on the size of the nucleus, how hard the nucleus is pulling on those electrons. And that's how we can tell what element is what in an X-ray spectrum. So it's the chemistry and physics of this haven't changed.